I'd like to welcome everyone. My name is Rebecca Lowe. I am the Adult Program Coordinator here at the Lewis Public Library, and thank you for joining us this evening. And welcome to our November Science and Society presentation, Making Sense of the World Around Us. This lecture series is co-organized and moderated by Fred Dilla, Executive Director Emeritus of the American Institute of Physics and author of Scientific Journeys, Linda Dilla, former Public Information Officer at the Jefferson Laboratory in the U.S. Department of Energy, and Colin Norman, the former news editor at Science. And one thing I forgot is I put in the chat our last in the fall 2025 Science and Society lecture series will be next month, Tuesday, December 4th. It is actually our esteemed Fred will be giving that. Dr. Dillo will be giving that presentation on fusion. So I put the link in the chat for that so you can find out more information and register. So with that, I will turn this over to Fred.
Thank you, Rebecca. It's good to see everyone on the Zoom screen tonight. We've been doing this series for 5 years and enjoying putting it together for you and enjoying your participation and many of your comments. And occasionally I get asked from you, explain what's this quantum mechanics thing? And now there are things called quantum computers and quantum entanglement. And what's it all about? Well, quantum mechanics is one of the two most important theories that were invented in the last century, the other being Einstein's relativity. And it's the bedrock of modern physics. But it's not easy to explain. So I've asked a good friend who I know does a much better job than I can of explaining some of these strange things that happen because of the quantum world. And you may be familiar from the general news that there are discussions of quantum computers that are based on quantum effects. So I'm going to introduce to you our night speaker. He's a good friend. It's Professor David Kaiser from MIT. He is from the History of Science Department, MIT. He has a degree in History of Science from that other school up the Charles River, Harvard, but then he came downriver to where he's had a very successful career. And we've interacted in many occasions and have enjoyed our interactions, which why I was very happy to reach out to David for tonight's talk. The title of the talk is from his book, which I hope you will get a copy of. It's got a great title, How the Hippies Saved Physics. And if you read one of the little burps on the back from John Gribben, who is another science writer from the Wall Street Journal, it says, "It's rare to find quantum physics mentioned in the same breath with sex, drugs, and rock and roll. I heartily enjoyed How the Hippies Saved Physics." Well, you will enjoy this book and you can get it from our local store. So David will start the story from the beginning and hopefully entice you to get the details in his really enjoyable book. David, the floor is yours.
Fred, thank you so much. I want to thank Fred and really all the organizers. I'm very honored to be able to join you, and I hope this will be fun and of interest for you as well. I'm going to go ahead and share screen. I do have a bunch of slides, and we can jump right in. So let me get myself organized here a little bit. I'm going to do the usual hide the controls and go to full screen. And so hopefully that looks good to all of you.
It's good.
Perfect. Okay, thank you, Fred. Okay, so as Fred mentioned, I'm going to talk with you tonight about how the hippies saved physics. And what I'm going to do is actually tell a story about some the kind of journey I've been able to take in studying this material. It is indeed based on the book that Fred just mentioned, with this kind of funny title and frankly rather obnoxious cover. I often have to tell some of my friends that's not the author photo, that's not me standing naked in the woods, but it is meant to evoke some of the kind of spirit of the kinds of things we're going to delve into a bit tonight. So the talk has three main parts. The first is a kind of warm up on some of the things that Fred was just telling us about, a particular feature of quantum theory called quantum entanglement. It's one of the most delicious and strange and in the end, powerful features of quantum theory. And I want to tell you a bit about that so that we can understand who cared about it, who thought that was important, where and when. That'll take us into this part here in the middle about the folks I wound up writing about for that book. And then near the end, I'll talk about some of the work that I did with some amazing colleagues in the last few years, trying to test in further detail, to further scrutinize this very strange sounding idea of entanglement. So the historical book actually helped to catalyze some new physics, even in recent years. And that's been, for me, a really remarkable adventure. So entanglement can be summarized this way in some words, is that two or more particles come so strongly interconnected according to quantum theory that actions on one of those particles seem to have an effect on its partner no matter how far apart they have traveled. And so why is that strange? Ordinarily, when we think about ordinary physics or our common sense or even the physics of Einstein's relativity, if we do something to particle A, we hit it with a hammer or we perform some measurement, whatever we do, we interact with particle A, it takes some time for information about that interaction to travel across space over time before any news of that could get to some distant particle B. And what's really strange is that the equations of quantum theory suggest this instant interconnection, this entanglement, which seems to not only break with common sense, it clearly is on a collision course with relativity, that great pillar, the other great pillar of modern physics that Fred had mentioned a moment ago. Albert Einstein and some younger colleagues actually helped to identify this as a prediction of the equations 90 years ago in 1935. And this was front page news in the New York Times that Einstein and his colleagues were attacking quantum theory, that somehow wasn't the full description. This was their formal article that we now simply refer to by the initials of the authors, Einstein, along with Boris Podolsky and Nathan Rosen. We still call this the EPR paper, published, as you can see, in the Physical Review, the main journal of the American physics community, in spring of 35. And this led to a series of decades of intense discussions and debates with close friends and colleagues like Niels Bohr. One of my favorite photographs. This is how I think physics maybe will be done again, relaxing with friends late at night, cigar smoke optional, but really trying to figure out how could the world work that way. This notion that there could be an instantaneous connection despite our ordinary experience and even despite other really important parts of physics like relativity. That to Einstein just seemed like a leap too far. He thought this was more like ghost stories than physics. And he famously said many years later, this was like spooky action at a distance, a phrase you might have heard before. Well, it turns out neither of those friends, Einstein or Bohr, wound up convincing the other of their position until each of them passed away many decades later. Fully 30 years after that original EPR paper, this younger physicist shown here, John Bell, originally from Northern Ireland, revisited that topic. You can see his extremely influential paper here on screen. You can see he's clearly zeroing in on that 1935 work by Einstein, Podolsky, and Rosen. This was published almost exactly 30 years later in late autumn of 1964. And it's a very elegant short paper. And what he does is basically point out that Einstein's conclusion that there's something rotten in the state of quantum theory, that really rested on two critical assumptions. And Bell wanted to zero in on those assumptions and see what we could do with them. The first assumption that Einstein and his colleagues had made that was critical to their conclusion in being critical of quantum theory was that each of those particles has some definite properties on its own before it's measured. I like to think of that in this cartoon version. If you imagine particle A sort of zigging and zagging through space, going on its journeys, then it's carrying with it a kind of logbook, or if you like, an instruction manual as shown here. So if we were to stop that particle on the street and say, what's your spin along the x direction? You might ask about one of its properties. It would simply have a definite answer. It could look up in its logbook and it would say, oh, it's spin up, or anything like that. That it has a list of definite properties before we happen to ask it those questions, before we subject it to measurement. The other critical assumption that Einstein and the gang had made was that nothing, including not even information, no force, no material particle, no information, should be able to travel across space arbitrarily quickly. There should be an upper limit. Typically, we think of the speed of light from relativity. It could be quick, but not infinitely quick. And what John Bell said was that these are actually assumptions. They seem quite reasonable. A lot of amazing physics has been built on top of those assumptions. But the conclusion that Einstein had drawn really rested on those assumptions. And Bell said, what if we try to test those assumptions instead of simply assume them to be true and then criticize the theory on that basis? So Bell set up a kind of cartoon version. John Bell was an extremely accomplished theoretical physicist. I like to joke that this is what experiments look like to theorists. This is what I think experiments look like. So a kind of cartoon version. And in John Bell's honor to this day, we call these Bell tests. So let me walk through the elements here that are in this kind of cartoon version. We have some source of particles. I'll call that S for source. And that source of particles can emit pairs of particles, which I'll call A and B, and they'll shoot off in opposite directions. And then we have these boxes, the details of which actually won't really matter for Bell's argument. So I just draw them as these kind of little generic boxes. At each box, a physicist over here, for example, can choose a particular property of particle A to measure. What that means here is she can choose to measure property 1 or property 2. She has a little dial, and she can set this arrow to be pointing toward property 2 or property 1. Identical device for her partner some distance away. She has an identical detector. She can now perform some measurement of her choice on particle B. Whatever question physicist 1 chooses to ask, the box will simply spit out one of two possible outcomes. Either the green light will flash or the purple light will flash. For those of you who have maybe a little more familiarity, we can make this concrete. We could say, for example, that this physicist over here at this device wants to measure the spin of particle A along some direction in space, let's say the x-axis or the y-axis. Her choice is to measure spin along the x-axis, set the dial here, or along the y-axis, some orientation in space. Really, how does she rotate her magnets, let's say? And then the particle arrives, and whatever question she'd set, the box says, oh, the answer is either +1 or -1, spin up or spin down. The green light flashed or the purple light flashed. Likewise for her partner, the other physicist at the distant detector. What Bell realized, which is really quite ingenious, is that we can actually compare how often the answers at those two detectors agreed, how often green light flashed with green light, how often purple light flashed with purple light, even if the physicist asked different questions. The answers will always only be green light or purple light, say +1 or -1, even if different questions had been asked at each device. So we can start making comparisons of the outcomes of the measurement answers, even as we vary the questions being asked. And what Bell demonstrated in merely 6 pages, it's a remarkably elegant, brief analysis, is that if the world behaved as Einstein assumed it must, that pair of assumptions that particles have definite properties, nothing travels arbitrarily quickly, then there's an upper limit to how often those answers can agree. And that's what I've shown as these green lines here. A certain quantitative measure, which we can use when comparing the answers from each box line up. If the particles each have definite properties prior to their measurement, and if nothing can zip across space faster than light, then in Einstein's preferred world, these answers from the two boxes would only ever line up so often, but not more. And what John Bell confirmed in this 1964 analysis was that quantum theory, the equations of quantum theory suggest there should be stronger correlations, at least for some clever choices of what properties to measure. So quantum theory predicts this solid dark gray curve, and you can see with these purple arrows, there are places where that would be violated. Einstein's assumption would be violated quite a lot, in fact, by about 40%. Not a kind of minuscule amount lost in the noise, a robust predicted signal. This looks like a showdown. This looks like exactly what Einstein and Niels Bohr and their friends had been missing back in the 1930s, 40s, and 50s, was a way to get beyond only late-night cigar smoke-filled debates and say, could we subject this to a laboratory test? So today, this argument from John Bell is literally renowned. That's a technical term to physicists. It means it's been cited more often than practically all other papers in the history of the field. It took a long time to get there. So here's a chart of all the citations, all the articles in the world's scientific literature that cited John Bell's paper over time. So the paper was published in 1964. 1 year later, zero citations in the world. In 1966, 2 years after publication, there was exactly one citation in the world, and that was a follow-up paper by John Bell. It was a self-citation. We'll take that out. No such, you see this, it's not taking the world by storm for years after the publication of what we now recognize as one of the most consequential, influential articles in the history of the field. You only start seeing some sustained attention, a dozen, maybe 2 dozen papers per year, fully a decade or so later, starting in the mid to late 1970s. So the article today is beyond compare, but it wasn't that way for a long, long time. Then you can do something else. You can say, well, who is actually writing these articles that actually were engaging with John Bell's work? Who was writing the articles that did the citing, that were engaging with Bell's article from 1964? And then you start seeing a very stark pattern emerge, in which I focused on then for this book. The authors in this sample were dominated by members of a small, informal, frankly, very quirky group based in Berkeley, California. They called themselves the Fundamental Physics Group. They spelled physics with an F, and that's what I want to tell you about, is some of their work and what they made of all these strange sounding ideas. To set the stage for that, let me start by looking at another curve that I stare at an awful lot when I wear my historian's cap. This is the number of PhDs in physics granted by every single university within the United States per year. You can read off really the kind of patterns of the Cold War from these bumps and wiggles. You can see the Second World War ends in 1945. That's followed by a remarkably rapid growth, an exponential growth in the number of young physicists getting their degrees. The US enters the Korean War in June of 1950. That leads to a temporary plateau. But then the Soviets launched the Sputnik satellite in 1957, and boom, off to the races again, another exponential rise in the production of young physicists. Meanwhile, you can see this doesn't last forever. I'm sure many on the call will know what's coming next or can make sense of it. With the escalation of fighting in the Vietnam War, all kinds of things began to change, of course, in the country at large, on US universities, and for the field of physics, perhaps more starkly than from any other field in the academy. So starting in the late 1960s, as the war was really dragging on, deferments for full-time students, deferments from the armed services, were getting revoked. That's going to start taking a hit out of enrollments. It was at first removed for undergraduates, then removed for PhD students. And then by 1969, in the wake of these widespread protests on many, many US campuses against the presence of military spending on university campuses, there was passed what's called the Mansfield Amendment, which again, some of you might remember, a congressional amendment that said that basically the Pentagon in the United States could not fund open-ended research on campus. It had to fund kind of research that was specifically in aid of the military. They couldn't fund open-ended basic research, which had been the lifeblood of physics funding really from this stage on. So you have draft deferments, you have budget cuts, you have all kinds of conspire, and physics begins to fall in an eerily symmetrical way as quickly as it had risen. Every field in the academy in the US fell or went into some contraction starting around 1970, but none fell quicker, harder, faster than physics. One a kind of concrete way that will be familiar to folks like Fred, I know, and many others of you. The American Institute of Physics, which Fred had led for so many years, began offering a kind of placement registry starting soon after the end of the Second World War to connect young physicists, especially during these boom years, young PhDs in physics, with employers looking to hire young physicists. And you can see the stats from their own placement registries. In the mid-1960s, even amidst this exponential growth in the supply of young physicists, the number of jobs outpaced the number of job seekers, even as the number of job seekers continued to rise. That was, a remarkable time to be entering the field. And yet, look what happened soon after that. By 1971, on this side of that kind of Mount Everest peak, there were more than 1,000 young physicists seeking jobs and only 53 jobs on offer in the entire country looking for young physicists. And that means university jobs, government laboratories, industrial positions, every single sector that was looking to hire PhDs in physics. There was a difference of about roughly 20 to 1 in the number of young students looking for jobs compared to the jobs on offer. That's the setting for this group that I wrote about called the Fundamental Physics Group. It was a group of folks who were very well trained in physics. Most had done PhDs from some of the most sort of decorated departments in the country. And their main miscalculation, though not their own fault, was to finish their PhDs just when the bottom fell out, just when that kind of Mount Everest spike turned into very, very bad territory for young physicists seeking jobs. So they kind of bumbled along in a different kind of hiccup sort of way. They found each other in Berkeley, California, and they, decided to get together and chat about things. They basically had time on their hands. Each of them had joined the field during these boom years of runaway growth, numbers of students, numbers of grants, everything was growing. And that led to what was often called a shut up and calculate era. It was said usually tongue in cheek. But the idea that these long-standing late nighttime debates between people like Einstein and Bohr, that those were somehow really not going to be what you should spend your time on, was the kind of overwhelming message that these folks had received when they themselves were undergraduates and PhD students in the 1950s and 60s. But yet, once the bottom fell out and they did not have typical employment of the sort they were looking for, they realized they still had big questions. They were drawn to the field because these what does it all mean kinds of questions, including at the foundations of quantum theory. And now they figured if they were not going to have a traditional career, they could at least try to go back to those questions that had drawn them to the field in the first place. The group was organized by this physicist here, Elizabeth Rauscher, shown in one of the control rooms for one of the big colliders at Lawrence Berkeley Laboratory, where she was doing her PhD. And as she explained to me many years later, she realized it would be easier to learn about all this material if we got together for informal discussions and lectures, as they did. They got together every Friday afternoon for years at Berkeley and then went out for a pizza dinner afterwards to talk about these grand mysteries of quantum theory. One of the core members of that group from the first time it started meeting was a gentleman here, John Clauser, shown here in his lab at the Lawrence Berkeley National Laboratory in the early 1970s. He and a then graduate student, Stuart Friedman, conducted the first ever experimental test of Bell's theorem. They actually did the first Bell test with a source of particles here, and then in this kind of duct taped, built on the cheap contraption, here's box one. They can measure one property of an entangled particle here, and there's the other device over there. They found exactly the kind of strong correlations predicted by quantum theory, exactly what Einstein assumed couldn't be there. This was the first actual empirical experimental test to show that quantum theory seemed to hold in the world after all. Well, it turns out members of that group were in the Bay Area in the 70s when all kinds of things were going on. And many of them got very excited about stuff that was being reported in the mainstream press all the time, especially in the Bay Area, in the San Francisco Chronicle, as well as in some of the more underground kind of pamphlets and newspapers and magazines. And their idea was to connect quantum theory, especially this kind of strange interconnectedness of Bell's theorem or quantum entanglement, to all kinds of other strange interconnections that were being reported, like parapsychology. That means things like telepathy or mind reading or all these kinds of things. They were further inspired by tests that were done at the Stanford Research Institute, a spin-off, mostly defense contracting lab that had until recently been part of Stanford University, and at the height of the protests against the Vietnam War was spun off by Stanford to be a standalone contracting laboratory. And in the early 1970s, this gentleman here, Uri Geller, a Tel Aviv stage magician who began pronouncing that he wasn't only good at stage tricks, he actually had genuine psycho, sort of ESP type abilities. He was whisked to SRI, subjected to laboratory controlled experiments by two other very accomplished physicists, the findings of which were published in peer-reviewed journals like Nature and the proceedings of the IEEE, showing what to these physicists' satisfaction, scientifically rigorous, statistically significant indications of things like telepathy and mind reading. So one of the members I'll talk about, Jack Sarfati, member of this Berkeley group, was brought in as a kind of theory consultant. He had a PhD in theoretical physics. He was following the latest tests of things like Bell's inequality and so on. And he began releasing these press releases, some of which I show here. He writes, for example, in describing these tests on Uri Geller, that the ambiguity in the interpretation of quantum mechanics leaves ample room for the possibility of psychokinetic and telepathic effects. He says, things like these particles stay connected across a great distance. That needn't be any more strange than the kinds of things that Geller seemed to be displaying. In a related release, Sarfati writes, my personal professional judgment as a PhD physicist is that Uri Geller demonstrated genuine psychoenergetic ability. Well, again, as you might expect, if you start saying things like that in the San Francisco area in the mid-1970s, a bunch of people get very excited. So these folks now, members of the so-called fundamental physics group, this is Jack Sarfati, who just written those press releases, Saul Paul Sarag, Nick Herbert, and Fred Allen Wolf in what they like to call their young Frankenstein pose. They became really media darlings, both for local coverage and also for nationwide press, like Time Magazine and beyond. The New Hampshire Sunday News covered the group really clear across the country. There was breathless coverage in places like City Magazine, a magazine based in San Francisco, that this group was, quote, going into trances, working at telepathy, and dipping into the subconscious in experiments towards psychic mobility, all, as far as the group was concerned, made feasible, made realistic in their mind because of phenomena like quantum entanglement. Now, how do you support this kind of work if you're not in a kind of traditional physics career, which these folks were not because of these huge disruptions to the profession? One way, which had worked really well since the late 1940s, was to tell the US federal government that the Soviets were doing it too. And this really goes to a classic Cold War playbook, in this case going to both the CIA and something called the Defense Intelligence Agency, which is actually formally housed within the Pentagon, but similar kind of work to the CIA. And there were at the original day classified reports, this one's since declassified thanks to a Freedom of Information Act request, that was alleging, based on the best intelligence they could gather, that the Soviet scientists were working on what they called controlled offensive behavior. And that really meant mind reading and mind control, kind of Manchurian candidate type stuff. That released some substantial funding for further-up study of what was jokingly called espionage. Could you use ESP, things like mind reading, to conduct espionage at a distance? Members of this group I was describing, like Elizabeth Rauscher, whom I showed earlier, and Jack Sarfati and Saul Passerek, they did their own follow-up tests published in open literature where it looked like they could really actually have statistically significant versions of what I'll simply call mind reading as a shorthand. And they would say this is actually plausible because of this long distance connectedness enabled by quantum entanglement. It wasn't only the federal government. Another thing that reminds us of the setting that they were immersed in this Bay Area in the 1970s, was to turn to some very generous and suddenly very wealthy patrons, what we might call, loosely speaking, New Age gurus. And this included people like Werner Erhard. Some of you might know that name. He was actually born with the name Jack Rosenberg, and after a kind of interesting series of career steps, he renamed himself Werner Erhard. He'd been fascinated by quantum theory. He'd read many popular books by Werner Heisenberg of the uncertainty principle fame. And so he took the name Werner from the German name Werner. Erhard was from a different inspiration. And he began working, what we might today call loosely a kind of self-help group, became wildly successful, commercially successful, and very, very popular across the country. Erhard was very, very interested in the nature of human consciousness and whether one could kind of expand or even, let's say, improve upon typical human consciousness. And he was convinced that these mysteries of modern physics, like quantum theory, could help us do that. He began rather generously funding this California group. And in fact, I found the articles of incorporation for a nonprofit group that could be funded with donations from people like Erhard to support the work of that fundamental physics group. They had a new home base, and that was another place that, again, might be familiar to some of you, called the Esalen Institute in Big Sur, California, nestled in the cliffs down the coast, just a little bit south of San Francisco. Here you can see this amazing photograph. And this was something that went on to become kind of famous for, let's say, ground zero for all things hippie, counterculture, and new age. Things that once seemed really radical, like vegetarianism, which might not seem so radical today, but once were, or yoga and these things. It turns out the longest running seminar series in the history of this place, which is otherwise known for these kind of classic hippie counterculture things, the longest running seminar series was on quantum entanglement and possible ties, not proven, but possible ties to things like power of mind, mind reading, ESP, and all the rest. Some of you might know the book, The Dancing Woolly Masters. That was written by the then roommate of Jack Sarfati, the science writer Gary Zukav. And Jack basically invited Gary down to spend the first month at the kickoff month-long physics session at Esalen. And Zukav's mind was so, blown that he wrote this book that went on to become a bestseller. The group, these physicists, remember, they had PhDs from really leading programs. They were underemployed, or at least not employed in the careers they wanted, but they still had deep questions about things like entanglement and whether it really could be made compatible with relativity. Could you use entanglement to beat relativity? Could you actually send messages faster than light? After all, it looked like this instantaneous connection, which Einstein railed against, but that experiments were showing in some limited sense, maybe really you could lean into and learn more. So here's a patent application that Jack Sarfati filed in the late 1970s for what he called superluminal, or faster than light, telegraphy. It's a very clever idea. Here's a page from that patent filing. He was going to use the exact same source of entangled particles that his friend and discussion mate, John Clauser, had just used for that experiment in the early 70s. He's going to send it toward two devices. I can go into more details if you'd like. But the upshot was, as far as Jack Sarfati was concerned, that anything that you could do here, including encoding a human voice in the pattern of those interference fringes over here, that pattern, thanks to quantum entanglement, should be instantaneously transmitted arbitrarily far away and show up through a sort of speaker. So it would be like an instant, kind of telephone call. And he says in the patent filing, this device could give instant communication between an intelligence agent, like in the CIA, and his headquarters, say at Langley. In this case, we would use correlated psychoactive molecules such as LSD to make sure that the brain chemistry was especially susceptible to quantum entanglement. I just want to make sure you understand what he's saying. You're going to get both the field agent and their handler hopped up on LSD so that their brain waves could be more kind of fruitfully entangled. And then one could go and sort of learn about, say, what the Soviets are doing, and the counterpart back at headquarters would have an instant communication link. It turns out the patent was not granted, and partly wise because of immediately local reasons. Another member of that discussion group, the fundamental physics group, in this case named Philippe Eberhard, who was a staff scientist at Lawrence Berkeley Laboratory at the time, also very curious, one of the few people very curious about things like entanglement before we all knew sort of we should be. He was actually talking every week with the group, and he realized that there's something that really should block this kind of instantaneous information exchange. He wrote this up. I want you to notice the journal it came out in a very good Italian journal, not in the Physical Review, because this was deemed merely philosophy, and the US journals wouldn't publish this kind of work. So Eberhard, though he was based at a prestigious US institution, sent his work overseas, and here's what he found. If all you have access to is you're sitting here with your measurement device, all you see is a random looking series of green lights and purple lights flashing when you set your detector to measure property 1 or property 2. If all you have is your kind of logbook of this, you have basically random noise. You have just zeros and ones in a completely random order. Your partner, on some very far distance away, all she has is a random sequence of greens and purples. That's like plus ones and minus ones. You only realize there was something very spooky going on when you bring both of those logbooks together and you compare what were the questions asked, run by run, what were the answers given, and then, only then, do you see this very strange, spooky correlation. So that the quantum entanglement was real, but was not something you could use to send a message, because if you only have access to this side, you just hear static. You literally have nothing but white noise. This was the first demonstration that even John Bell himself hadn't known would work out. the first demonstration that this very spooky quantum entanglement really is compatible with relativity. There's something strange happening at arbitrary distance, but it's not information exchange. It's not a force traveling from one side to the other. And so there's some uneasy truce that seems to hold between these two pillars of modern physics. And there were many other things that were done afterwards that led to things that are now literally, sort of page 1, 2, and 3 of our textbooks. It came from this quirky group pushing very hard on this question about entanglement and asking kind of open-ended, sometimes philosophical or out there sounding questions at a time when they felt like they had nothing else to lose. Now, I want to shift gears briefly and tell you what happened after my book came out, because this led to another adventure that I just am so dearly grateful for. The book came out, and then soon afterwards, this gentleman here, Andy Friedman, who had just done his PhD in astrophysics at Harvard and was going to do a postdoc with me in physics at MIT, he read the book, I assume because it had a funny looking cover. And he talked about the book with his friend from grad school, Jason Galicchio. They'd both been in physics together. They began talking about the book at a Nobel establishment in Harvard Square called John Harvard. It's basically a burger and beer joint. And they realized, because they were both trained in astrophysics and cosmology, which is my own field in physics as well, that we've learned a lot about the structure of space and time, about how events have evolved in the fabric of space and time over the whole course of cosmic history, much, much, much more than was known at the time of either Einstein and Rosen or at the time of John Bell. So together, they talked with me about it. I was Andy's supervisor on physics, and we wrote this paper saying we could actually start doing a new kind of test of the sort that Bell had in mind, but while closing what's called a loophole and try to make an even more kind of stringent test of quantum entanglement, which after all seemed to be so strange, but also so important. Let me come back to this cartoon version of a Bell test. What we were thinking about is often called the freedom of choice loophole. When we think about tests of these entangled particles, we imagine performing some local random choice, like flipping a coin, to decide what property to measure. Whether we're going to set this to be pointing toward, say, the x direction or the y direction when we want to, say, measure particle spin. We're supposed to have free choice of what to measure. Our colleague far away has some what's supposed to be uncorrelated free choice of her own, flip her own coin to choose to measure, say, property 1 or property 2. What happens if, unbeknownst to us, there was some common cause, some third party? I like to think of these kind of Dick Tracy characters, who somehow either got hold of our coins and gave us like trick coins or had some way of previewing the answers and sharing the outcome of the coin flip with the source of particles before the particles had been emitted, right? That's like cheating. That's like a student getting the pop quiz the night before so she knows exactly what question she'll be asked in what order. If the student has a copy of the pop quiz ahead of time, like these folks sharing the information with the source particles ahead of time, then it's not so surprising, perfectly consistent with an Einstein universe, for these measurements to line up, because the particles, in a sense, would know what they'd be asked when. They could make a plan together before they left, home. Say on question number 7, make sure you say green and not purple. If there's some common cause in the shared past, then suddenly an Einstein-like universe would lead to these spooky-looking correlations, even though it was perfectly normal, not quantum mechanical after all. This was pointed out to John Bell by people like John Clauser, members again of that Berkeley discussion group, a dozen years after Bell's famous article. And he responded saying, oh, you're right, I'd overlooked that. I'd assumed there was no such correlation, but actually we should think about that. More recent, more modern work, including by me and my group and other physicists, showed that if you allow for this kind of correlation, this kind of third party whispering in the ears to give a heads up of what questions would be asked in advance, then you can actually design Einstein-like models that would very, very easily reproduce all the predictions of quantum theory, even though it's not actually acting according to quantum theory. So how do you guard against that? And that's what Andy and Jason and I had proposed. We call these cosmic Bell tests. So very briefly, in the last few moments, I'm going to tell you about what we had in mind. The idea was to outsource this random coin flip, not to a coin, say, in our laboratory, but to the universe itself. We wanted to turn the universe into a pair of random number generators because it's about time the universe did some work for us, is what we thought. The idea was to take some beautiful large telescope, point one telescope in one direction of the sky, point a separate telescope in the opposite direction of the sky. After the particles have been emitted from the source, after the entangled particles have been emitted, but before we perform measurements on either one, we perform a very rapid observation of cosmic light from a very, very distant, faraway galaxy, a quasar, some of the most distant light sources we can measure. And depending on the properties of that light, which we measure while these particles are in flight, that tells us what question to ask of this particle when it finally gets to its detector. We're outsourcing the randomness to events that happened long ago and far away. We pitched this idea to this gentleman here, Anton Zeilinger, when he was visiting MIT. He immediately had a grin, at least as broad as what is shown here in this photo. He loved the idea. Anton went on to win the Nobel Prize, by the way, along with John Claus, another colleague. Anton had already built a remarkable career testing quantum theory in these remarkably ingenious ways. He loved the idea. We loved that he loved the idea. A new friendship and partnership was born. So with Anton and his incredibly gifted group of experimental colleagues who really can make entangled particles, perform these rapid measurements, along with myself and Andy and Jason and other friends on the astrophysics and cosmology side, we could put together this new thing that we called cosmic bell tests. The idea, as I said, was to use enormous bright galaxies from which light has been traveling toward the Earth almost since the time of the Big Bang itself, for billions and billions of years. So long ago that there was no way to know what question would be asked until a fraction of a second before the particle arrived. Here's what our experiment actually looked like. We did this on a beautiful mountaintop observatory in the Canary Islands, the island of La Palma. And here's where our paper came out with this large group of amazing colleagues. Our experiment had three main centers. I'm going to talk about this transmitter site first, and then these two distant telescopes on the mountaintop observatory. Inside this shipping crate, that literally is a crate that we shipped from Anton's laboratory in Vienna, there was two main ingredients: a laser tuned to a very specific frequency, actually about this color purple, shining onto a very special piece of material called a nonlinear crystal. That's just fancy talk for saying one particle of light comes in, two particles of light come out. That's how we make our pairs of particles. They're born in essentially one event. One photon comes in, and because of the atomic structure of this crystal, the crystal absorbs that one particle, uses the exact same amount of total energy, but splits that energy into a pair of particles. They then can be zoomed out across the island. They head toward these two absolutely gorgeous telescopes sitting about half a kilometer apart each from our main station here. The Galileo National Telescope, the William Herschel Telescope. These are two of the largest optical telescopes on the face of the planet. They have 13-foot polished mirrors, 4-meter collecting plates. Absolutely gorgeous instruments that the astronomers dearly love, and they generously loaned to us for a few nights. So what happens when you use these telescopes to look at light that's coming from a very distant source, like a very distant quasar? The quasar has some average color. The light from that quasar comes out with an average frequency, but there'll be little jitter, a little bit of fluctuations, more blue or more red, if you measure that light over very short windows of time, a little fraction of a second. So sometimes the light comes out as more blue, sometimes more red than the average or typical color. What we decided to do was take a real-time measurement of that quasar light and then perform an extremely rapid manipulation if the light during a tiny, basically a millionth of a second, a microsecond window, if the light from the distant quasar happened to be more blue than average, then we set our on-the-ground detector to measure, say, property 1 of the incoming particle that we made from that laser across the island. If, on the other hand, the light from the quasar happened to be slightly more red during that little split-second interval, then we measure property 2 of the incoming particle. The point is, this choice is made after the entangled particles from that laser have already left the station, before they can kind of make a plan. There should be no way for them to cheat by getting the equivalent of a copy of the pop quiz ahead of time. We did this with 20,000 pairs of particles across that mountaintop. It was just a thrill. And we found exactly the spooky correlations that were predicted by quantum theory, despite what Einstein would have hoped, dreamed, or expected in his heart. even though the decisions of which measurements to form property, measure property one or property two on each of those particles, those decisions were literally unknowable even in principle here on Earth until the tiniest split second before the experiment was conducted, and that was set in stone 8 billion years ago. No one, that we could think of could have kind of messed around with that quasar light to set up the correlations we'd measure today. So the decision of what measurements to perform was set up before Albert Einstein was born, before there was an Earth, even really before there was a Milky Way galaxy. We're using most of cosmic history to outsource, to separate as much as possible in space and time, this random choice, and yet we still find this extremely spooky quantum behavior. So we can't attribute that to a kind of Einstein-like story where someone got the pop quiz in advance. So let me wrap up, and I look forward to talking more with you. For more than half a century now, the work by John Bell has served in at least two ways to help us clarify really deep questions. It's enabled us to explore the foundations of quantum mechanics, like spooky, strange, counterintuitive features like quantum entanglement, and also to explore the changing boundaries within physics itself. How do physicists sit within wider culture? What counts as a legitimate question to pour your resources into and not? So both the world can be a complicated place, the world of scientists can be complicated. And what I found so juicy was that this topic of entanglement and John Bell's work could help us explore both of these kind of in parallel. So I'm going to pause there. I'll stop sharing screen, and I look forward to talking with you about that work.
David, thank you very much. Let me lead off with the first question. Have some people give some time to put their questions in so I can see them. I should point out your famous graph of the number of physicists who got their degree versus time that peaked in the year that I started graduate school. So I was very much part of that. And my undergraduate and my graduate work was funded by the Department of Defense. That's why that curve turned around.
Yes.
But the question I have is, you started out by telling us that Einstein and Bohr had these wonderful philosophical discussions in the 20s and 30s about what is the meaning of quantum mechanics and the particular detail about this spooky action at a distance.
Right.
Why did that discussion disappear until these hippies in Berkeley picked it up 50 years later?
Well, Fred, that's a great question. First, I'll say cheekily, have I got the book for you? So I do. It's a very important question, one I thought about a lot. And so before I prattle on for 3 hours, I'll say briefly that that's really important for the whole setup. I skipped over it here in the interest of time, but it's really tricky. And that was some of the most fun I had working on the book, was really trying to delve in to things like changing curricula, changing textbooks, changing general exams, and how they were evolving across the United States. Let me also make a plug for a group that you and I both love, the AIP. They made my work easier as an historian because they, even back then in the 1950s and 60s, were deeply interested and concerned about how the nation's PhD programs were training young physics students. Were they kind of, comparable? Were there patterns to be found? Were some places doing one thing very differently than others? And so even back in the 50s, let alone Fred, in the era when you were running the shop as well, they were running surveys and questionnaires of most departments of physics across the country. So I could just go to College Park, to this headquarters of the wonderful library, and go through the collected kind of surveys that were sent in by departments across the United States, saying, here are the courses we require of the PhD students, here are the typical exams we give, here's an example of our general exam, here are problems. Amazing, rich set of material to show really a rapid change in how young physicists were being trained in this country between, let's say, the 30s and the 50s and 60s. The short answer to what is described in more detail in the book, but the short answer is that the Second World War happened, as you know. That had a big impact on many ways. One thing that in one way that had an impact was it drove this exponential growth in the field after the war, that curve that you saw growing exponentially fast. In fact, physics enrollments grew faster than any other field. Every field in the American university grew exponentially after the war. This was the time of things like the GI Bill. There was sort of federal funding to encourage students, especially veterans of the war, to go and seek higher education where many might not have had the opportunity before. And yet, even as the entire university system grew exponentially, the exponent for physics was twice as large. Physics was screamingly fast growth compared to everyone else. That outstripped, say, the growth of, say, the number of instructors and so on by manyfold. And you see this again reflected in things like the AIP surveys and as well as individual correspondence and so on from the time. So what that meant was class sizes grew, even for PhD students, very, very rapidly. So whereas, I don't know, Fred, about your experience, in my experience, when I did my PhD in physics in the 1990s, I would have, say, 2 dozen students in an advanced graduate seminar or graduate class. Some of these classes in the late 1940s and throughout the 1950s had 100 PhD students in a course, say, on quantum mechanics. Now, those of you who have teaching experience might appreciate you teach differently if you're teaching a seminar of 12 students versus a kind of auditorium packed to the gills of 100 students or more. You don't assign essays to 100 students unless you have a lot of help grading and so on. So I want to be clear that the argument I'm making is not good, bad. It's different. There were styles of engaging with extremely difficult physics. These people were extremely well trained coming out in the 1950s. They were trained differently. Different skills were accentuated, and I think at least in part, I think a large part actually, because this really kind of very sudden shift in the kind of classroom realities, not just for undergraduates, but even for PhD students. And that's what led, again, semi-tongue-in-cheek to the so-called shut up and calculate. You can test whether students have figured out how to solve for the behavior of a single electron in a hydrogen atom on a problem set in a way that's harder to say, discuss the kind of philosophical implications of the fall of determinism in 3 paragraphs, right? And so you start accentuating different types of very hard, very important skills, and that has a kind of cohort or generational effect. That crashes when the enrollments have this sudden downturn. And again, you look at things like textbooks published in the 70s, look at a shift in general exams, and suddenly when classes are returning to very small numbers compared to what had come before, you start seeing come back into the official curricula things that sound more like open-ended essay questions, something more like the meaning of it all. So I think we can get a lot of this kind of push and pull from thinking about the settings in which we have trained generations of physicists.
Well, thank you for giving a plug to my former institute in all our data collecting. Glad it was useful to an esteemed historian like yourself. Let me bring it down to a more practical question.
Yeah.
So studying entanglement disappears for 50 years, and now it's suddenly in the vogue because it has some practical applications. Could you tell us a little bit about how these practical applications may play out in the future, and what are they?
I'd be glad to, Fred. So there are many, but let me mention at least 2, and others might have others in mind as well. The first one, again, I wrote a bit about in the book because it really comes out surprisingly directly from the developments that I was just describing briefly just a few minutes ago. And that's what we now call quantum encryption or quantum communication channels. This is the one that's, frankly, of all the quantum technologies, the one that's among those that is most advanced, not quite off the shelf commercial, but getting, I'd say, remarkably close, much closer, say, than quantum computing, for example. The idea is indeed to use these properties of entangled particles, exactly the kinds of particles that the hippies were studying, the same kind of particles that my colleagues and I were studying many years more recently with these cosmic Bell tests, to produce a channel of communication that is secure against hackers. The main idea is that these special entangled or connected correlated properties, that's actually very fragile. If anything intervenes with one of those particles, it will kind of dissolve or dissipate that special connectedness. And that means if you start doing tests of entanglement of the sort that people now do, now with laboratory precision, and you find that these particles are no longer entangled, then someone's hacked your line. Now that means that they've gotten only random noise. The intruder has not gotten your secret information, You haven't gotten it either, but you've been tipped off. And so basically the special connectedness of those particles can be disrupted if a third party intervenes. Everyone gets noise. You know someone's hacked. The information is secure. That's been demonstrated now over and over again in increasingly real world settings, in consultation with private sector banks and voting, electoral organizations and so on. It's getting close to being really robust. And so, anyway, so that's really, I think, the closest one. The other main one that you did mention yourself, Fred, is something called quantum computing. And that also typically involves these specially prepared entangled states where you can have parts of the system kind of explore many, many, many possibilities in parallel through this sort of strange interconnectedness of quantum theory. And that can lead to hyper efficient algorithms that can do certain kinds of tasks, not, like checking my email or playing, Wordle, but other very specific kinds of things we want to do with computers. It can speed that process up exponentially by basically having these entangled particles each explore possibilities, kind of, let's say, roughly speaking, together. It's very vague, but the idea is that this could really lead to a remarkable speed up of certain kinds of computing. And that would be resting on these very kind of quintessential quantum properties as well.
Well, it's fortunate that we might get quantum encryption at the same time as quantum computing because
Right.
quantum computing will make ordinary encryption not work, right? So
Exactly. That's one of these tasks at which quantum computers would be especially, quick at
yeah.
cracking. And then, just as you say, we would then have this kind of quantum arms race, potentially, of encryption, that of quantum encryption being maybe the answer to quantum computing that could break ordinary encryption. Exactly right.
So we have a question from Rob Koenig. Is there a potential for AI to speed up the development of quantum computing?
It could be. There are experts on that, and I'm not one of them. So experts in many places, including MIT. That's certainly an ambition. What I often hear about it is sort of the inverse, actually, where quantum computers, if and when they really become reliable and stable, could actually help us understand other things more readily. That maybe even, let's say, powerful but still conventional AI could not. So quantum computers could lead to what we call quantum simulators to simulate the behavior of quantum matter because that becomes extremely complicated and bogged down, even on our fanciest, best conventional computing devices, which also drive things like AI. So honestly, I think there is an opportunity for AI and enhanced quantum computing. What I find most interesting when my colleagues tell me about it is the inverse of that, making these quantum computers that could simulate genuinely quantum matter, and that could lead to things like protein folding and maybe even breakthroughs in pharmaceuticals, real world things that could really be of widespread benefit. And those are one of the things that people are eager for in an era of quantum computing.
I'm glad you mentioned that. I'd like to remind this audience that the first protein structure that was ever analyzed by Max Perutz in the 60s, 70s,
Mhm.
it was almost 25 years of work and 10,000 X-ray diagrams. There are thousands of proteins that make us work and make us not work. And being able to do that in a matter of weeks will speed up, as you mentioned,
Right.
our understanding of biology and medicine. So we almost out of time here, but one question from Susan H. What are the next questions to be explored in this very esoteric topic you've introduced us to?
Well, I think part of why I find this so delicious, I mean, literally delicious, is that this topic leads, on the one hand, to very concrete devices, the sort we've talked about just briefly here in the Q&A, quantum encryption, quantum computers, quantum sensing, that people really are already taking advantage of, and then I think will only accelerate. So on the one hand, we get to actual gadgets that really like could be genuinely helpful and hopefully genuinely beneficial. And on the other end of that, it leads us to still deeper questions about the very structure of our understanding of nature at its core. And I just find that endlessly fascinating. So, for example, we do not yet know how to combine quantum theory with Einstein's great scientific pillar, the general theory of relativity, his theory of gravitation. Many, many people are beginning to wonder, no proof, but wonder is the ultimate structure of space-time itself actually a kind of property of quantum entanglement? We describe entanglement as having this kind of uneasy relationship with relativity. Might it be that deep, deep down, what we think about as kind of Einstein's smooth, gentle, continuous space-time, could that be an artifact, a kind of averaging of what under the hood would actually be a kind of dense network of quantum entangled something? We don't know, but that's the kind of question that Bell's theorem and even these tests that my colleagues and I were able to do can further sharpen, even though it doesn't quite answer them for us. So you have this incredible range from I want to make this new thing and make a patent and study protein folding and make better medicines. Amazing. I want to protect quantum communications, all the way to how do we quantize gravity and what's the ultimate nature of space-time itself? And this is just the gift that keeps on giving because the topic sits at this kind of midway point between all these very important directions.
So the last question comes back to your title. Did the Werner Erhards of the world and the other psychics that got interested with the Berkeley hippie group, did they actually advance scientific inquiry? And does the Pentagon still have an interest in paranormal phenomena?
Good. So for the second one, I can say simply, I don't have clearance and I don't know. And I won't even hazard a guess. I don't know. For the first part, that's something I really tried I really sat with that. Well, again, while writing the book and even since then. What I think the upshot of this, the kind of colorful 1970s work and 1980s work is that these were often mistakes, and that's okay because all the scientists we study made a lot of mistakes. Einstein made more mistakes than not. When he was not making mistakes, they were pretty great, but he made lots of mistakes. Marie Curie, Richard Feynman. So I don't fault any of these folks for doing things that today we might not consider the best final answer. But these were productive mistakes. These were generative of new ideas. And that, I think, is extremely valuable. And these were not being done on their own, for which I think the genuine generosity of people like Werner Erhard and Michael Murphy at Esalen and other patrons, I think that really had a positive outcome from our viewpoint today. Not that we have to endorse every one of their enthusiasms, but we can see careful, disciplined study by people who had done the homework and done the careful study, even as they were inspired by a broader set of questions than maybe was typical. They could frame questions that simply weren't being asked before. If their pet answer didn't wash out every time, they could catalyze and inspire others to dig in because the question had been framed in a very, very sharp and answerable way. And then, with hindsight, we can see that really did lead to things we just didn't know about before, things like what we call the no cloning theorem, quantum encryption, and beyond. So what I find most kind of delightful about this story is that the hippies, as we can call them, the group that was working with great joy and great skill, both, were pursuing questions that might not be my questions, but those questions were in the end productive. And we don't, as I say, we don't have to endorse everything they tried to appreciate someone was trying and was asking questions beyond shut up and calculate. And I think that is a legacy we should really pause and recognize because we have, as a whole community, learned a lot because of those efforts.
Well, thank you, David. That's a good comment to close on. And I remind people, you want to hear more, get the book from Browse About or your local independent bookstore. You'll enjoy more of this. So before I turn it over to Rebecca, who will open your mic so we can thank him, David, stay on the line with Colin and I after everyone signs off. So over to you, Rebecca.
All right. Thank you, everyone. And thank you to our presenter. So as is our custom, if you would like to unmute yourself and applaud and say thank you, we would love for you to do that. So just go ahead and say thank you.
Thank you.
Thank you.
Thank
Very
you.
much.
Very good.
Thank
Thank you
you.
very much.
Thank you.
Actually appreciate it. Thank you.